Many times, thinking and acting in directions opposite to common beliefs is a fruitful means of making discoveries. Real evolution is not in thinking and trying. Perhaps it lies in making up from one's long sleep.
Meanwhile, scientists have awakened a 46,000-year-old
A study published in PLOS Genetics Journal in Tuesday 2023 highlighted the gene sequencing of a microscopic female roundworm that spent the last 46,000 years in suspended animation deep in the Siberian permafrost. It was revived and started having young ones in a lab. The science behind this time-traveling nematode and the strategy it adopted to go dormant to survive extreme environments for 46,000 years is a matter of deep revelation. The concept of suspended animation, which involves pausing an individual's biological processes, has been a theme for a number of science fiction movies.
120 years hibernation means we'll wake up in a new century on a new planet. But a year ago,
the blockbuster Avatar, directed by James Cameron, showed characters using suspended animation pods to travel long distances through space to reach the distant planet Pandora. Growing interest in this field can be traced back to the 1950s, largely fueled by the enthusiasm of the space race. A group of scientists began a new adventure with the objective of exploring the feasibility of inducing a state of artificial preservation in humans. The primary aim of this pursuit was to safeguard astronauts from hazardous cosmic radiation prevalent in outer space, as well as to significantly reduce logistical burdens such as food, water, and oxygen, thereby enhancing the viability of extended space missions. In a groundbreaking trial in 2019, Dr. Samuel Tischerman and his team at the University of Maryland School of Medicine in the US successfully tested suspended animation in humans for the first time as part of a trial aimed at addressing traumatic injuries that can be fatal. This revolutionary experiment involves the swift calling of individuals with severe traumatic injuries with the goal of extending the window for surgical intervention, thereby providing additional time for surgeons to save critically injured patients. Blood loss due to bleeding is primary contributor to fatalities during surgical procedures, formerly known as emergency preservation and resuscitation, or EPR. This procedure is presently being tested on individuals who have sustained catastrophic injuries, putting them at risk of bleeding to death and experiencing a heart attack shortly before they can receive medical treatment. These patients, often victims of stabbings or shootings, would typically have less than a 5% chance of survival. In suspended animation, an animal's body slows down its essential functions without stopping them completely. The technique involves rapidly lowering the brain's temperature to below 100 degrees Celsius by substituting the patient's blood with an ice-cold saline solution. Typically, this solution is introduced directly into the aorta, the primary artery responsible for carrying blood away from the heart to the rest of the body. The rapid cooling of patients significantly reduces brain activity to almost a complete standstill. This will slow down the patient's physiological processes, providing surgeons with valuable additional minutes, possibly extending to over an hour, to perform necessary surgical procedures. Once the patient's injuries have been addressed, they are gradually warmed up and resuscitated. Therapeutic hypothermia is now commonly used in hospitals to reduce injury in a wide variety of situations, from surgery to helping infants recover following difficult births. Of course, this is not that simple. Hypothermia can be a dangerous condition. Our body wants to be warm and will fight to remain that way. Throughout our lives, our body generally maintains a relatively stable temperature of approximately 37 degrees Celsius, a task that demands significant effort. It continuously makes many adjustments to equilibrate heat production with the heat loss to the surroundings, striving to preserve body temperature within a narrow range. If it decreases beyond this threshold, blood is redirected from the skin to the central torso, causing us to shiver and seek warmth under blankets. The effects of more severe cold are disastrous. at a body temperature of around 33 degrees Celsius, just 4 degrees below normal, our heartbeat begins to flutter. At 25 degrees Celsius, there is a risk it will stop altogether. And even if we survive hypothermia, warming once again can cause extensive kidney damage. On the other side, lowering one's body temperature has the effect of slowing down metabolic activity, diminishing it by approximately 5 to 7% for each degree of temperature reduction. Consequently, the pace at which essential nutrients such as oxygen are consumed also decreases. This phenomenon offers protection to tissues that might otherwise experience oxygen deprivation due to factors like blood loss or cardiac arrest. Theoretically, if we were to continue lowering our body temperature, there would come a point where our biological processes would come to a complete halt. This would result in a state akin to suspended animation, much like a stopped clock. There would be no physical ailments afflicting us. All internal components would remain intact, merely in a state of immobility. The sole requirement for reactivation would be a modest application of heat. Some insects, amphibians, mammals, birds and fish possess the ability to diminish their metabolism, entering states of low energy to survive in extreme situations, like when they don't have enough oxygen, or even when it's extremely cold or when it is summer. The state marked by decreased body temperature and reduced activity is referred to as torpor, slowing down the biological time in relation to the clock time. During suspended animation, animals become inactive by chaining together multiple brief episodes of torpor. These animals can transition into the extended dormancy phase with absolutely no intake of food and water, without urine or waste production for an extended period. However, when hibernating, these animals can withstand much more severe injuries than they would under normal body temperatures. This resilience stems from a combination of factors, including the safeguarding of tissues due to reduced metabolic rates and considerably slower pumping of blood by the heart compared to its typical rate. When an animal or plant spending the winter in a dormant state, it's called hibernation or winter sleep. The Arctic ground squirrel normally maintains a body temperature similar to our own, but during hibernation can survive at core temperature as low as -3 degrees Celsius, carefully managing its super cool bodily fluids so that it won't freeze solid. How animals survive these states is of great interest to anyone hoping to unlock the secrets of suspended animation for humans. Scientists found that when they rapidly cooled animals by pumping ice-cold fluids into them or using machines called cardiopulmonary bypass (CPB), it helped protect their organs, especially the brain. However, cooling the body too much can have some negative effects like making the blood more acidic, causing problems with blood clotting, making inflammation last longer, and weakening the body's ability to fight off infections. So researchers are interested in finding drugs or other ways to safely induce suspended animation when needed. In reality, when a person is critically ill or with severe inflammation, the organ function will be reduced, and this may be an adaptive response to save energy rather than a sign of permanent organ damage. This is because the body can conserve energy when it's not working much. Prior to entering into a lengthy hibernation period, animals consume a lot of food, essentially becoming similar to humans with type 2 diabetes. However, unlike in humans, this doesn't lead to thickening of artery walls that causes heart disease. Some species even stop eating a couple of weeks before hibernation, becoming resistant to hunger despite maintaining their usual activity levels. While a human can experience muscle loss and blood clotting after just a week of inactivity in bed, hibernating animals endure months of immobility. During hibernation, the community of bacteria living in an animal's digestive tract, called the microbiome, faces challenges due to the cold and sudden lack of food. Hibernators develop thick layers of mucus and collagen in their lungs, similar to those seen in people with asthma. It was very interesting to know that their brains undergo alteration that resemble early-stage Alzheimer's disease. In some cases, hibernating animals lost their memory. What's even more surprising is that some display symptoms of sleep deprivation when they wake up from such a long sleep. Despite all these challenges, hibernators manage to overcome these issues and recover in the spring, often without any long-term negative effects. Hibernating animals avoid getting blood clots despite their lack of activity. Hibernating animals avoid getting blood clots despite their lack of activity, an ability that comes down partially to a curious change in the hypothermic body. As the cool platelets disappear from the blood, nobody yet knows where they go, but their prompt reappearance on rewarming. Surprisingly, this change also happens even in non-hibernators, including rats and occasionally human victims of hypothermia. The shared characteristics of different hibernators mean it's likely that these species have inherited fragments of protective mechanisms against cold, inactivity, starvation, and asphyxiation from common ancestors. Studies show that as body temperature drops, hibernators also remove the lymphocytes, a type of white blood cells, from the blood and store them in the lymph nodes, and within 90 minutes of awakening these reappear. This damping down of the immune system prevents a general inflammation in the body during rewarming, the very thing that would cause humans and other non-hibernators to suffer kidney damage. Knowing how hibernators control these changes in the blood could have immediate and far-reaching benefits for us, as well as improving our ability to survive hypothermia and cold suspended animation. While cooling has a uniform impact on all body tissues, it's not without its secondary consequences. Cold also hinders the blood components responsible for clotting, leading to difficulties in managing bleeding during the rewarming phase. Throughout the procedure, both the patient and the room itself will be chilled. The approach here is to akin biomimicry, where we harness nature's remarkable adaptations to serve the betterment of medical applications. However, it's essential to recognize that cold is merely a tool. The ultimate objective is to achieve metabolic suspension. Certain experiments conducted in mice showed that inhaling hydrogen sulfide could induce a reversible suspended animation like hypometabolism and decrease energy expenditure. This fall in metabolic activity was associated with abnormally slow breathing rate and consecutive hypothermia. After washout of hydrogen sulfide, all these metabolic and cardiopulmonary effects were completely reversible and the animals showed no apparent sequelae. But the effects on energy metabolism remain a matter of debate. A prominent figure in suspended animation research is NASA, the National Aeronautics and Space Administration of the US. Together with SpaceWorks, NASA has been hard at work in this field since 2013 on a project entitled Torpor Inducing Transfer Habitat for Human Stasis to Mars. The scientists try to induce suspended animation in humans via a state called cryogenic sleep. As per scientists, cooling is the most effective technique we possess for slowing down metabolism. By either decreasing the metabolic demands of tissues or improving the supply of oxygen to them, outcomes can be significantly enhanced. Inducing suspended animation in humans presents one set of challenges while safely reviving them from the state poses another. Researchers are actively exploring ways to achieve this transition effectively. The achievement of suspended animation in humans could extend the window of opportunity for surgeons to perform crucial procedures when blood circulation ceases. And it could also make the dream of long-distance space travel a reality. Amid the hot desert landscapes of Scottsdale, Arizona, in the US, almost 200 bodies of humans are cryopreserved at the Alcor Life Extension Foundation facility, packed in cylindrical tanks filled with liquid nitrogen at minus 196 degrees Celsius. These human bodies are waiting for a revival in the hope of awakening into new era beings. Let's hope science will uncover the underlying mechanisms involved in this intricate process. Hope you like this video. Like, share and subscribe our channel. We'll meet soon with yet another informative video. Till then, stay tuned. Thank you. Godspeed.